Welcome back viewers. Today we will see sequencing of n job 2 machines in operations research. In this video we will study what are the assumptions of sequencing, how to make use of Johnson's algorithm for sequencing, tie-breaking rules and calculation of elapsed time and idle time. One of the important assumption in sequencing is that one job can process on only one machine at a time. Processing sequence we cannot change, and processing times are independent of the sequence of the jobs. And very important assumption is that if the job is loaded on machine, then it must be continued till end. Now let us see the Johnson's algorithm. Johnson's algorithm is very simple to understand. It states that if the minimum processing time is for the first operation, then the job should be placed first in sequence, and if the minimum processing time is for the last operation, then the job should be placed last in sequence. Let us try to understand this Johnson's algorithm with an example. Here you will find there are 5 jobs, and we have been given the processing time for these 5 jobs on machine 1 as well as machine 2. What we have to do is you have to search for the smallest processing time, and you will find out of this smallest processing time is 4, and this 4 is for job 1, and this 4 is the last for the last operation. So as the smallest processing time is for the last operation, job 1 is sequenced at last. Once this job is sequenced, we have to consider only the remaining jobs. Now, out of remaining jobs, the smallest processing time will find is 6 on machine 1, that is for the first operation on job 4, and therefore job 4 is sequenced first. Then you will consider the remaining 3 jobs. Out of remaining 3 jobs, you will find the smallest processing time is 8, and it is for the last operation for job 2. So job 2 is sequenced last. Then you will find out of 3 and 5, the smallest processing time is 9 for the first operation of job 3. Hence job 3 should be sequenced first, and job 5 only one slot is there, so it should be sequenced at that slot. In the previous example, there was no tie, but there is a possibility of having ties in the smallest processing time. So you will find in this example of 6 jobs, the smallest processing time is 2, and it is for machine 1 as well as machine 2. Hence, as per this tie-breaking rule, if the smallest processing time is for the first operation, job should be sequenced first, and if the smallest processing time is there for the last operation, job should be sequenced last. So this is how the tie can be broken. It is very simple. But sometimes there is a possibility that the tie is for the smallest processing time, and it is for both machine 1, that is the first operation. So which jobs to be sequenced first, whether 3 or 6? For that we have to refer to the processing time of last operation. Now you will find though the processing time is same for the first operation, processing time is different for the second operation, and what we can do is we have to select the job with the lower processing time on second operation to be sequenced first. So though this tie is broken, looking at the lower processing time for job 2, and hence job 3 is to be sequenced first, and next job 6 is sequenced. Similarly, there is a possibility of tie for the second operation. So you will find job number 1 and job number 4, they have the equal smallest processing time for last operation. So how to decide which jobs to be sequenced last? For that we have to refer to the processing time of job 1, and whichever job is having low processing time, that will be sequenced last, because the smallest processing time is for the last operation, and hence job 1 is sequenced last, and then in the remaining slot we will place job number 4. So this is how tie can be broken. Let us see how to calculate the total elapsed time as well as idle time for the same exercise that we have just completed. First column, we have to write the optimal sequence we have obtained using Johnson's algorithm. Then machine 1, machine 2, we have to load the job first on machine 1 and then on machine 2. So you will find the job number 5 is the first in sequence, and it is having 2 units on machine 1 and 11 units on machine 2. So on machine 1 it is started, okay, and after 2 units job is completed. Once it is completed on machine 1, it will be transferred on machine 2. where it takes 11 minutes. So after starting 2 units, it will be completed after 13 units. Next in sequence is job number 3, which is having 5 units on machine 1. So it can be loaded on machine 1 as soon as first job is over, that is after 2 units, and then it will take 5 units and it will be completed after 7 units. Then job 3 is to be taken on machine 2, but I cannot take immediately after 7 units because machine is still busy doing the previous job. So it can be loaded on the machine 2 once the previous job is over, that is after 13 units. It takes 9 units. So after 13 units, if we load job number 3, it will finish by 22 units. Same exercise we need to follow. Okay. If the machine is waiting for the job, then that is considered as idle time for the machine. And so you will find in this whole exercise, for the first 2 units, machine 2 does not have any load because it is waiting for the job to be completed on machine 1. So 2 units is idle time on machine 2, and total processing time or elapsed time is 48 units for all 6 jobs. So in this video we have studied how to do the sequencing of n job on 2 machines. In the next video we will study the sequencing of n job on 3 machines. Thank you for watching video. Okay, we'll meet again for the next video. Thank you very much.